So, what if I told you that some of the most famous algorithms out there actually succeed by being, well, greedy? They just take the best-looking option right in front of them, and somehow they still manage to land on a perfect optimal solution.
And that's really the core question, isn't it? What if making the best immediate local choice at every single step could actually guarantee the best possible outcome in the end? It's a seriously powerful and, frankly, very appealing idea.
But, and this is a big but, it's a gamble. Because the simplicity is so alluring, it can be really deceptive. Sometimes that obvious choice right now leads you down a path you just can't recover from, locking you out of the true best solution. Check this out. This is the perfect example of that trap. Take the classic coin change problem. We need to make the amount 6, and we've got coins worth 1, 3, and 4. The greedy approach screams, take the biggest coin first. So you grab a 4. But now you're stuck. You have to add 2 1s, which gives you 3 coins total. The optimal solution? Just 2 3s. The greedy choice literally painted us into a corner.
Okay, so if it can fail that easily, when can we actually trust this approach? When is being greedy not just a good guess, but provably, mathematically, the best thing to do? To prove a greedy algorithm is the real deal, we use this absolutely beautiful technique called the exchange argument. Here's how it works. We start by assuming there's some better optimal solution out there. Then we find the very first place where its choice is different from our greedy choice. Then we show that we can swap its choice for our greedy one without making the solution any worse. We just keep doing that until, piece by piece, we've transformed that supposedly better solution right into our greedy one. It's brilliant.
And listen, this isn't just some clever trick. It's backed by some seriously deep mathematical theory. Things called matroid structures, for example, are special problem types where a greedy approach is guaranteed to be optimal. The cut property is the entire reason our network building algorithms work so well. And for a whole class of problems with diminishing returns, greedy gives us a mathematically proven approximation. This is the formal seal of approval.
All right, so let's get practical. Let's build our greedy toolkit with a bunch of powerful patterns you can use to solve a huge range of problems. First up, we've got a category you're absolutely going to see in coding interviews: problems that involve intervals and scheduling.
The classic example here is activity selection. You've got a list of events, each with a start and end time, and you want to attend as many as possible without any of them overlapping. The greedy rule here is so simple but so powerful. Sort all the activities by their finish time. By always picking the activity that finishes the earliest, you're guaranteeing that you free up your schedule as fast as possible, which maximizes the time you have left for more activities.
Next, let's dive into the world of networks and connections with some killer patterns for optimization and graph traversal.
Now, this is what I find fascinating. You can have 2 totally different greedy strategies that solve the exact same problem. So let's say you want to find the cheapest way to connect a set of cities. That's a minimum spanning tree. Kruskal's algorithm looks at all possible connections, globally, sorted by cost, and just keeps adding the cheapest one that doesn't create a loop. Prim's algorithm, on the other hand, starts at one city and grows the network outwards, always adding the cheapest link to a new city. 2 different greedy rules, both perfectly optimal. How cool is that?
And of course, we have to talk about the legend, Dijkstra's algorithm. Its greedy choice is to always move to the closest unvisited node. This simple idea is the foundation for everything from how data packets are routed on the internet to your car's GPS. But, and this is a huge but, it has one critical weakness. It only works if all the path costs or edge weights are non-negative.
Okay, but what about those monster problems? The ones that are so computationally hard that finding a perfect solution is basically impossible. Well, that's where our third pattern group comes in, when getting close enough is actually a massive win.
Okay, look at this number. It is incredible. For a whole class of really tough optimization problems, we're talking NP-hard problems, a simple, greedy algorithm is mathematically guaranteed to get you a solution that is at least 63.2% as good as the absolute perfect one. Getting a performance guarantee like that on such hard problems is often the best we can possibly hope for, and that makes it incredibly valuable.
And you have to know, this stuff is built on a legacy of some seriously deep theoretical work. This quote from Jack Edmonds back in 1971 really cemented the connection between the simple greedy idea and the profound mathematical structures, those matroids we mentioned, that guarantee it'll work.
Okay, Theory is great, but how do we translate all of this into a clear, confident answer in a high-pressure coding interview? Let's break it down.
Here is your playbook, your 4-step checklist to absolutely nail the answer. Number 1, state your greedy rule loud and clear. My greedy choice is to sort by end time. 2, name the data structure that makes it fast, like a min heap or a disjoint set union. 3, briefly justify why it's correct. Even just saying, this is provable by an exchange argument, shows you know your stuff. And 4, this is the pro move, acknowledge the pitfalls, the cases where your solution would fail.
Okay, let's tackle the big one, the question everyone asks. When do I use greedy and when do I use dynamic programming? Here's the deal. Greedy makes a choice and commits. It's final. It never looks back. DP, on the other hand, explores all the options and then picks the best one. Think about the knapsack problem. For the fractional version, where you can take parts of items, greedy is perfect. Just take the stuff with the best value-to-weight ratio. But for the 0-1 knapsack, where it's all or nothing, a local choice can be a huge mistake. You need the exhaustive power of DP for that.
All right, so let's bring it all home. When you're staring down a problem and you get that greedy feeling, what is your next best choice?
Look, it really boils down to this. Define your greedy rule. Justify why it's correct, either with a quick exchange argument or by citing a known property, and then pick the right tool, the right data structure for the job. If you can master this 3-step process, you're going to unlock a massive class of algorithmic problems.
So we've seen just how powerful and elegant making the right local choice can be. I'll leave you with this thought. What problem, maybe in your code or even in your life, are you going to solve by focusing on making the next best choice?